Hello, welcome to chapter 12. Uh, Stars and Galaxies is the last chapter for 8th grade science. The last chapter was just specifically about our solar system, but now we're going to go into what actually is a star. How can we tell the difference between stars? What are stars made of? How do stars work? And all that jazz. So let's go and get started with lesson 1. Basic question, what are stars? Stars are a large ball of gas that emits energy produced by nuclear reactions in its interior. You guys might have heard it described as like a giant ball of fire. It's not really fire, because for there to be fire, oxygen needs to be burning. It's not fire. It's nuclear reactions, and nuclear reactions are different than chemical reactions. So fire is chemistry, but the things that are happening on the inside of a star, that's nuclear chemistry. It's the nuclear reactions. They follow different rules than the stuff we learned about earlier in this book. Now, the light emitted by these stars enables us to see other objects in the universe. We don't see the sun because light is hitting it. We see the sun because it's giving off light. And the part of the sun that is giving off light is called the photosphere. And that's just, it's like the surface of the sun. The sun doesn't really have a surface, but if it did have one, it would be the photosphere. And our star is pretty normal. Medium-sized star with a temperature of 5,800 Kelvin, which is about 10,000 degrees Fahrenheit. Kelvin is just the way astronomers use to, and chemists use to measure temperature. It makes a lot of the equations work out a lot nicer than using Fahrenheit or Celsius. We don't need to know how to use it to get Kelvin or anything like that, but just know that when we talk about Kelvin, we're using it on purpose because it's easier for astronomers and chemists to do math in Kelvin than in Fahrenheit and Celsius. If you did not know, the sun has like a bunch of bubbles on it. Like this is what the surface of the sun looks like. It's all these weird little bubbles everywhere, and these bubbles are kind of like if you can imagine a boiling pot of water. How sometimes the water rises and then falls, and it makes all those little currents and stuff like that. That's pretty much what's happening on the sun, except instead of water, it's a bunch of really hot plasma and gas. Here's a typical cross-section of something like our sun. We see the photosphere, or the surface of the sun. It's at about 6,000 Kelvin. Followed by something called the convective zone, which is at 1 million Kelvin. Followed by something called the radiative zone, which is 2.5 million Kelvin. And then we get to the core of the sun, which is about 15 million Kelvin. That's a pretty insanely high temperature. Because remember, this is 10,000 degrees. Now, there are stars that are all sorts of shapes, and not shapes, I'm sorry, all sorts of sizes. We have like regular stars, you could say, and then we also have things called supergiants. They are, I don't think you can actually understand how large they are. I'll show you a picture of what it means in a second, but they're so big that like our solar system can fit inside of a star. Not just our sun, but literally from our sun to like Jupiter. All of those planets, all of that empty space could fit inside some of these stars. A slightly smaller supergiant called a red giant starts about the size of our sun, but later it gets to be about 100 times the size of our sun. So imagine our star, but way bigger. That's what a red giant would be. Here is a blue supergiant. So you can see that little yellow dot right there, that's the sun. We would be around this ring. Jupiter would be around this ring. So all of this could fit inside of this star. Now, Earth is already pretty big to us, regularly speaking. We know the sun can fit all sorts of Earths in there. So imagine how many Earths can fit inside this blue supergiant. Earth is like smaller than a grain of sand compared to this blue supergiant. We have other strange things called neutron stars that are only kilometers in diameter, but are more massive than the sun, which means, imagine like something the size of Riverside or the size of LA or something, but it weighs more than the sun. That's how big neutron stars are. They are as small as a city, but they weigh more than the sun. And something else we need to be like keeping in mind when we're talking about stars is that all stars are ridiculously far away. In fact, instead of using things like astronomical units, like I said, like it tries to here, we go one bigger and we say, all right, well, instead of saying the distance from the sun to the earth like an astronomical unit, let's just say the time it takes light to travel a year and call that a light year. And that equals 9.5 trillion kilometers, or 63,000 astronomical units. So if you were at Earth and you went to the sun and you did that 63,000 times, that would be 1 light year. That's a very long distance. In case you did not know, light does take time for light to travel from one spot to the next. So technically speaking, when you turn on your light, the light has to shoot out of like your lamp and then hit you, and it has to travel through space in order to hit you like that. It just happens so fast that to our slow brains it looks instant, but like according to physics, that actually took a very, 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 very small amount of time to hit your eyeball from your lamp. The same thing with the sun. The sun is hitting you with light right now. Maybe not right now, but if you were to go outside, that light left the sun like 7 minutes ago. It took 7 minutes for that light to leave the sun and then eventually hit you. So if the sun just turned off right now, you wouldn't know for about 7 minutes because all that light is still heading our way. So we're dealing with distances that start like breaking down the stuff that we normally think about is true, because we need to remember all of these crazy new science rules that are being introduced. So if we look at a regular star, they can be anywhere from 10% of the sun's size to 15 times the sun's size. And they can be anywhere from 2.4 thousand Kelvin to 50,000 Kelvin. All those are considered normal stars. We see them called main sequence. But the red giant that we talked about, the red giant is going to be 10 to 100 times as big as our sun. It's going to be at 1 to 4 times the mass of our sun. And it's going to be actually probably cooler than our sun. Supergiants can be all over the place. That's why the temperature is variable. But notice it's at least 100 times bigger than our sun. We also have something called a white dwarf, which we did not specifically talk about, but that's another strange type of star. It's a lot smaller than the Earth. It's probably about the size of the moon, you can imagine. But it weighs as much as the sun does. And it's way hotter than the sun. So again, white dwarf and neutron stars are really weird. They're really small, but they weigh almost as much as our sun. But they can be either ridiculously hot or, I mean, you see variable, so it can be anything with a neutron star. So there's quite a few different types of stars out there. It's not just ones like our sun. Here's a couple of examples of our, you could say our neighborhood stars, the stars closest to the sun. The closest star to us is Alpha Centauri. That is 4.3 light years away. Which means if that star right now stopped shining, we would still be able to see it for 4.3 years, because the light that left that star takes 4.3 years to get here from there. That's how long it takes the light to go. That's how far the star is. Let's look at Sirius. It takes 8.6 light years, or it's 8.6 light years away, so it takes 8.6 years for light to reach us. So if you were in a spaceship and you were going the speed of light, the fastest anything can go, if you're in a spaceship and you're going the speed of light, it would take you 6 years to get to Barnard's star. It would take you 11.4 years to get to Procyon. I don't know how to pronounce that, but that's how far these things are. Stars are incredibly far away from each other. So, as a reminder, where does the star energy come from? You might say fire, but remember that's not true. They're nuclear reactions in the sun's core. So what are stars made of? Well, a long time ago, I brought out a spectroscope in class. I had like a neon sign, and you guys had those little black triangles that you would look at it, and it would split it up into a bunch of different colors. That's called the spectroscope. It's an instrument used to study the light. Obviously, the ones studying stars are going to be a lot fancier than the ones we had in the classroom, but the idea is the same thing. They're looking at the stars with this specialized equipment that will split up all of the light into its different colors. Speaking of different colors, if you have something like the sun, really hot, dense object, it's giving off what we call a continuous spectrum. And you'll see a picture. What that means, though, is that it's giving off a bunch of different types of radiation, all continuously, meaning you'll see the picture. There's like no gaps in what it's shooting out. Our star gives off a continuous spectrum because it is a hot, dense material. If you shine sunlight through a prism or through like glass or crystal, it splits up into a rainbow. You guys have probably seen that. I know a lot of people hang like little jewelry in their cars, so maybe when the sun hits the little piece of jewelry under the rear view mirror, maybe you see a bunch of rainbows. Or if you a piece of glass outside might do this. What's happening is the sun is a hot source emitting a continuous spectrum. If you were to break that light up using a prism, you get a continuous spectrum, meaning you get all the colors of the rainbow. Now, technically, there's even more stuff going this direction and more stuff going this direction, but our eyeballs can't perceive that. Our eyes cannot see those wavelengths, those types of light. They're there, they exist, but we cannot see them. We can only see a continuous spectrum. We can make computers and devices to detect this stuff over here and over there, but our eyes cannot see them. So that's a continuous spectrum. Now let's think about an absorption spectrum. And this is one of these. But you'll notice in the definition it says it contains dark lines. And the reason why it has dark lines is because imagine sunlight passing through a really big cloud on the way here. You know that if sunlight passes through a cloud, it gets a lot more dim, or maybe you can't exactly see the sun. Well, if there's one of those clouds out in space, it's probably not going to be as thick as the clouds here. So most of the light's going to get through, but some of these specific colors get stuck in that cloud. So not all of the colors hit us where we are. That is what an absorption spectrum is called. Okay? You can almost think about clouds of gas acting like a color filter and stopping certain colors from coming through. So if we were to get that filtered beam of light, we would see that some colors are missing. Those specific colors line up to specific elements, which means every element has a specific filter, which means we can directly tell which elements that gas cloud is made of based off of colors that are missing. And by doing that, we find out that most stars are just really hot hydrogen and helium. There's a couple other things in there for sure we'll talk about, but most stars are mostly hydrogen and helium. So here's a example of what I was talking about. We have a hot light source. Pretend this is the sun. If the sun were to just hit you with regular light, and you break it up in a prism, you get a continuous spectrum. You get all the colors. If you shoot sunlight through a thin cloud of cool gas, it's going to act like a filter, like I said. So instead of a rainbow coming out on the other side once we hit it here, we get a rainbow with some lights missing, some colors missing. You can think of like this gas essentially captured those colors. Okay? And then if we look at it from over here, if we look at only that gas and not this, but only the gas is emitting those colors that it stole from over here. So this gas essentially stole the colors from this sunlight and spat out the color as its own. This is how scientists can look at stars and tell what they're made of and what their temperature is. So the sun does give a continuous spectrum, but right around here, the sun, right around here, the sun has an atmosphere that kind of absorbs some of the colors. So if you have really delicate equipment, you can see which parts are missing, and you can see what elements that the atmosphere has. Now, the reason why you don't see this when you see a rainbow is because you don't have your eyes can't tell can't see those missing pieces. Okay, but scientists using super fancy computers and everything can break it down to like the smallest components possible, and they can see the parts that are missing from the rainbow. Our eyes can't though, but the scientists' gear can. So what is the difference between a continuous spectrum and an absorption spectrum? Remember, a continuous spectrum has all of the colors, but the absorption spectrum is missing some colors because they got filtered out. Now, something that might be strange is that something like the star is giving off a bunch of light, and that's, I mean, you guys are used to that, but technically every object emits energy in the form of electromagnetic radiation. Every single object that we know of pretty much emits some type of light. Our eyes might not be able to see it, but again, certain devices can detect it. The hotter an object is, the shorter the wavelength of radiation it emits will be. What that means is it's going to be bouncing around a lot faster. So the hotter an object is, the faster the light is bouncing around. You could think of like that. Because blue light hops around a lot faster than red light, we know that stars that emit blue light are hotter than stars that emit red light. So here, after a bunch of nerds did a bunch of math, here's the average. This is just a super general. If it's a red star, we know its temperature. If it's a blue star, we know its temperature. So no matter what, if you ever see a blue star and a red star, you know which one is hotter. The blue star, by definitions of like physics and chemistry, the blue star has to be hotter than the red star. Now this is talking about stars, not just about like paints and colors and stuff like that, but specifically stars. A red star and a blue star always have the relationship of the blue star being hotter than the red star. Yellow is hotter than red, white is hotter than red and yellow, but blue stars are the hottest stars. And I'll say it again. This is not just regular colors. This is for like stars. When we're saying electromagnetic spectrum, something that you might not realize is that there's different types of light. It's not just the light you can see. You guys may have heard of UV rays that are like dangerous to your skin or whatever. That's also a type of light. So you know if you get sunburn, it's because of these UV rays. You can't see them, but you still put sunscreen and wear sunglasses to protect yourself from UV rays. Some of you guys have maybe heard of infrared goggles or something like heat vision. What that is just looking at the types of reds that we cannot see. They are lower energy than red, okay? So right now you are giving off infrared light. You can't see it, but you are giving it off. But heat vision goggles can see that type of light, and they just smush it around until we can see it through a computer. If you ever get an X-ray, that's just a different type of light that they're shooting through your body. You cannot see that light. Our eyes can't detect X-rays, but it's a type of light. Microwaves. In your microwave is a type of light. You can't see the microwaves, but it's there. Radio waves. If you can pick up a radio station right now, that means those waves are hitting you right now. So if you could see radio waves, you can imagine how chaotic it would be because every radio station spitting out every type of radio program imaginable, you could see that. But we can't see that. And that's probably a good thing because it'd be all sorts of stuff. Your phone, your cell phone, your internet, your Bluetooth, all that stuff is shooting out a bunch of light in the form that we cannot see. We can detect it, like that's how you get Wi-Fi signal because your device says, hey, I can pick up the electromagnetic radiation coming from your router. It's all just a type of light. We can only see this little bit though, but it's all electromagnetic radiation. X-rays, UV rays, infrared, microwave, radio, Wi-Fi, all that stuff is all electromagnetic radiation. We just only see a very small fraction of it. And we interpret it as colors. Here's a mind-blowing fact. The closer a star is, the brighter it looks. Duh. That's like saying the closer you are to a lamp, the brighter it looks. But this can get confusing because some stars might look like they're really close, but they just happen to be gigantic and really far away. So we have to break it down. Instead of just talking about brightness, sometimes we talk about luminosity. And that's a number. That's how much energy a star emits per second. We measure that in terms of joules, which is a unit of energy. And then there's two ways to measure brightness. We have apparent magnitude and absolute magnitude. So apparent magnitude is how bright apparently the star looks. And the absolute magnitude is if we took all the stars and lined them up next to each other, which one would be the brightest? This might sound a little strange, but the more negative, the smaller the number, the brighter the star is. Okay? So let's go through these one more time. Apparent magnitude is how bright the star looks at night. Just apparently, how bright is it? But the absolute magnitude is if we could take all the stars and line them up right next to each other, which ones would be the brightest? So let's think about the sun. The sun is a star. It's ridiculously bright. And remember I said, the smaller the number, the brighter it is. So the sun's apparent magnitude is negative 26.7. That's a really small number, which means it's really bright. Hopefully none of you need to be reminded that the sun is really bright. Stars out there like Sirius, Canopus, and Antares, if we look at them at night, they have apparent magnitudes of negative 1.5, negative 0.7, and positive 9. So we know the smaller numbers are brighter. So we know that out of these three stars, Sirius is the brightest, Canopus is the second brightest, and Antares is the dimmest out of these three. But if we were to line them up all right next to each other, the Sun, Sirius, Canopus, and Antares, all right next to each other in a line, using a bunch of math, we would figure out that the actually brightest star would be Antares with a negative 5, because remember the smaller number means brighter. Then Canopus would be the second brightest star, then Sirius, and then the Sun would actually have a 5, which is not negative at all, which means it's actually kind of dim. So this is why apparent and absolute are a little confusing. Apparent is what it looks like to us on Earth, but absolute magnitude is what it would look like if they were all ranked next to each other. Okay? This is the same way, like, you might be the smartest person in this class, but if you compare yourself to everybody in the world, there might be a decent amount of people who are smarter than you. The same way, the sun is the brightest star we can see, but if you compare that star to all the other stars lined up next to each other, then the star doesn't really seem, our sun doesn't really seem nearly as bright. Let's look at a couple other stars. I've heard it pronounced two ways, Betelgeuse, like the old movie, or Betelgeuse, Bellatrix, Saiph, and Rigel or Rigel. I'm not sure. Apparent magnitudes are all positive numbers, but if we all line them up at the same distance, all stars, including the sun and everything, these guys would have negative numbers, which means these stars, while to us they look pretty dim, if they were all the same distance as our sun, these guys would be ridiculously bright. They'd be brighter than any of these, because these have a small, negative 7 and negative 8 are smaller than any of these. So these are way brighter than our sun. So a quick checkup, which has a higher surface temperature, a red giant or a blue main sequence star. Hopefully you guys remember when we're talking about stars. Bluer is hotter. Red is not. Red is cooler. Now this is a pretty long section, so we still got a decent amount, a couple more slides actually. Let's classify the stars. Quite a while ago, two scientists at the same time, almost at the same time, developed two fancy charts. Their names were Hertzsprung and Russell. A bunch of other smart people decided, hey, wait a minute, if we combine your graphs, we can just get one really, really complicated and nice one. So they did, and they get something called an HR diagram for Hertzsprung and Russell, HR diagram. And this allows us to classify a lot of the stars easily. Now, about 90% of the stars out there, including our sun, is what we call a normal star or a main sequence star. And that falls on a diagonal line on the HR diagram. There's a couple other groups of stars, but 90% of them lie on that diagonal line. The other groups we have are the red giants, the supergiants, and the white dwarfs. So here's a really basic version of the HR diagram. 90% of the stars are in this weird, right here, this weird thing. Whoa. Right here, 90% of stars. We have some red giants up there, we have some supergiants up there, and we have some white dwarfs up there. You can see that the higher you are this way, the brighter star you are. And the farther you are this way, the cooler temperature you are. All right? Which means the highest brightness is up here, and the highest temperature is back here. So these stars are the brightest and the hottest, and these stars down here are the dimmest and the coolest. Over here are really bright, but you'll notice that means they have a pretty low temperature. And then these white dwarfs are a little strange. They're not nearly as bright as anything else, but they're pretty hot. Way hotter than anything over here. Here's kind of like a picture of what some of these might look like. This is mostly in regard to color, though. Not really size. Supergiants are way bigger than this compared to our sun. But we see these blue stars are the brightest and the highest temperature. And these really small red stars are the dimmest, almost the dimmest, and the coolest. What is the definition of luminosity? Hopefully you guys remember that's the amount of light energy emitted per second. That's it for lesson 1.